completed her BE from Indian Institute of Engineering, Science and Technology, a very well-known institute at Shibpur, and Masters and PhD from Indian Statistical Institute, India, all in computer science. And she was an associate professor at ISI before she joined New South Wales, ISI Kolkata. And she also served as an assistant professor at Indian Institute of Technology, Indore. She has been a visiting researcher at New South Wales prior to joining this, NTU Singapore, KDDI R&D Lab Japan, University of Wollongong, Australia, IRIA France, Kyushu University Japan. These are all top-notch universities and institutions of research and higher learning. And she has also been an intern at Microsoft Research Labs India. Talking about her research interests, she has contributed significantly in the area of applied cryptography, blockchain and data privacy. And she has also served as program chair, co-chair for IndoCrypt. Those who are new to this area I would like to tell you that IndoCrypt is a very prestigious conference, ACISP 20T1, and she is a founding member of ACIS CCS workshop series, blockchains, cryptocurrencies, and contracts. And she has several awards and distinctions to her credit. She won the Best Paper Award at ISPA 2007, IEEE PIMRC 2011, IEEE ANDS VIE Women in Engineering 2017. She has also received Samsung GRO grant, NetApp Faculty Fellowship, Cisco University Research Grant, OCSP grant from IBM Research, and she is a senior member of ACM and IEEE. Well, so many things are there which are, in this short span, because I hope that all of you are so keen to listen to her. So I would like to end here. And on behalf of all the academies, Sushma ji, participating academies at IIT Kanpur, IIT Roorkee, MNIT Jaipur, NIT Patna, and IIT DM Jabalpur, I welcome you to this program and request you to please continue.
Thank you very much, Professor Roja, for the introduction. Nice, kind introduction. So before I start the talk, I would like to thank the traditional owners and custodians of the land from where I'm speaking from, and pay my respects to the elders past, present, and emerging. So just to give a brief
recording in progress.
To give a brief overview first of what you can expect from this talk, I would essentially talk a bit about some of the useful cryptography tools that are used in blockchains in the first part of my talk, and then I will switch gears to talk more about storage aspects in blockchain and some of the applications in storage that have also been helpful with the progress in the blockchain technology. So with that introduction, let me start this talk. So please feel free to stop me at any point of time if you have any questions or comments. I would really like this talk to be as much interactive as possible. And I hope that, if you have any questions, you can just unmute. Is it possible to unmute and ask the question, or maybe write in the chat window, and Professor Roja can just interrupt me and ask the question. And it will help so that, as and when we proceed, it will just be helpful because if you have any questions and I take it up then and there, it's much easier to proceed through the entire lecture. Okay, so in the last few days, by now you have realized that have got some idea of blockchain. So what I'm going to do, I'm not going to talk what a blockchain is and what are the underlying, what are the various components in the blockchain ecosystem. But what I'm going to do is just talk a little bit about the history of blockchain and how cryptography has influenced the current blockchain economy, I would say. A very funny thing nowadays is that when people talk about crypto, they mean cryptocurrencies. And recently realized or recently read that it has now also been included in the Woolens Dictionary. It's kind of funny because growing up, or when I was a student, and then for a very long time, when I say crypto, I mean cryptography. So when I see cryptocurrencies, crypto becomes synonymous with cryptocurrencies. It is a kind of a little bit hard to digest, but I realized that the cryptocurrencies and the underlying technology blockchain has become very, very popular now, and many things have become synonymous with this. But at the same time, I would like to mention that at the foundation, one of blockchains is cryptography, and many of the things that you have seen in the last few days are based upon various nice cryptographic primitives that have been there for a very, very long time. And so to start with, maybe I'll just mention that, okay, hold on. Just try to... Just trying to stop the share.
On the top of the screen, if you can see, yeah.
Yeah, no, I can see everything. However,
there new share. Yeah.
Yeah, I can see everything. I'm just not being able to
Okay.
exit from the screen. Okay, let me. What's happening here? Okay. Okay, now I got my cursor back. Now it's easy. Okay. Okay. Yeah, I think it's fine now. Okay. Yeah. So if you notice that there were various underlying primitives that were already there. For example, hash functions, digital signatures were there as early as the 1970s, mid 1970s, and as you might have already come across the Byzantine generals problem, which is at the heart of the consensus algorithms that you have, that was also there for a very long time, since 1970s, late 1970s. Another very interesting tool or primitive was also present, which is called secure timestamping, which is also at the heart of the blockchain technologies. Earliest form of these currencies were the DigiCash, which was proposed by David Sham, and it was one of the early, or I would say precursors of the cryptocurrencies or digital currencies. You might have also noticed that the proof of work that has already been discussed in the last few days was already there in 1990, since 1992, proposed by Cynthia Dwork. And you would also notice that the proof of work at that point was not meant for applications such as the blockchains, but at the time it was used for filtering spam messages. Now, later there were also various precursors of these cryptocurrencies, e-gold and so on. And then in 2008, Bitcoin was, the Bitcoin white paper came out, and people were just like in the midst of a financial crisis, and they found this very interesting cryptocurrency which claimed to be decentralized. There were no need for banks and financial institutions, trust on financial institutions, and very coincidentally it became very, very popular because at that point of time many people had lost their faith in the traditional financial institutions. So it was a very right time for the technology, and it flourished. And not only did we have Bitcoin, but the underlying technology was used for many, many purposes. And in the last few days, you have seen quite a few applications and how do you realize these sort of blockchains, various constructions, various types of blockchains. You have learned about Ethereum, Hyperledger, and the techniques underlying Bitcoin cryptocurrency. So I'm not going to go into all of those, but just a recap of what you have possibly studied is that the Bitcoin is a shared, replicated, verifiable ledger, and this essentially means that you will have this blockchain or the ledger replicated in multiple peer nodes in such a way that you could actually, if you were to tamper one blockchain and one ledger, then you would have to tamper in all the nodes, which is really, really impossible. So the couple of very interesting concepts that are underlying this blockchain technology is that it is distributed. It's a distributed ledger, meaning that the same ledger is written on various nodes in the blockchain nodes. Meaning that if you write, and because the reason for you cannot erase is that it is designed in a way that you can, if you want to erase it, you have to erase all the subsequent information that is present in that ledger. And not only have you got to change the subsequent information in one ledger, but you have to do it in all ledgers. And if you assume that majority of the nodes are honest, majority of the parties maintaining the ledger honest, then it becomes clear that you can actually make it immutable. The last part of it is that this ledger has to look the same in all the nodes, and you try to bring a consensus among the nodes so that they are all on the same page. They maintain the same copy of the ledger. So these are some of the key concepts. But what I haven't told about is the that are also present as a system. And so when I think of blockchain, it becomes extremely a very nice, synergy of various disciplines. Be it the underlying network mechanism, be it the distributed nature of the system with the distributed computing. As well as several other features that I will be talking about in the next part of my talk are very, very much dependent on underlying cryptographic mechanisms. So what I'm going to do now is tell you a little bit of building blocks the cryptographers are typically used. Used in this case is in the blockchain. And the second thing that I'm going to talk about is that how they are possibly used in a blockchain, and on the more advanced audience, I will also say some of the research challenges around these problems. What are the open questions around these? A lot of research and development are going on in this domain, and it's actually very difficult to keep pace with all of this. Just as an aside, I'll mention that when I started working on blockchains, that was way back in 2014, 2015. There were a handful of research papers, white papers, a few organizations doing blockchain. Now I see it everywhere, and it has been very tough to keep with the latest development and research, the latest challenges in blockchains, and it is now being talked about, it's been utilized, and it's being innovated. There is a lot of innovation going on in this domain, and what I'm going to do is just give you some very basic ideas, so that whatever you find interesting, you can pursue or read up more, and at least understand why these tools are important and why they are used, and what can be done with these tools in order to design new blockchains, adding functionalities to existing blockchains, and making things secure and privacy preserving. So I see that there are messages on chat, which is okay. So Professor Oja, what is the best way to deal with the questions? Is it, because I cannot read all the...
What I do is that after, say, half an hour, 45 minutes, I take up the question.
Okay.
Otherwise, what happens that we cannot further go. There are sometimes so many questions.
Okay.
That is my way.
Yeah, sure. Thank you. So I will take a break in the middle of the talk and discuss some of the questions that are there in the chat.
Okay.
Yeah. And you might have also realized that that a lot of information is being written on the blockchain, which is a big challenge when it comes to the scalability of blockchain. So, while designing blockchains, a lot of stress is used in providing scalability, in addressing scalability, performance, and security and privacy of the underlying networks. So when you look into the scalability issues, it's a scalability at different levels. It is scalability at the underlying designs. It is the scalability, and in order to address these scalabilities, you cannot just address because by making a block size much larger, because many blockchains have also restrictions on what information you could actually write on the blockchain, because of a specified block size that is prescribed for that particular blockchain. So keep in mind that one of the questions that we will be talking about in this talk would be that when we write data on the blockchain, these become these would become very heavy. So what we would typically do is that we would have some mechanism to address this sort of problems in blockchain. So that would be the second part of my talk, where I'll talk about the storage issues on the blockchain. But one of the primary motivation of that is that you cannot just put in everything in the block, because the blocks have specified capacity. Not only that, you might have also realized that while in the blockchain during blockchain communication is a big challenge, because you are broadcasting messages. So the less amount of information you broadcast, the better. And that essentially makes us ask this question: is that how do we minimize the amount of information that we communicate, that is communicated amongst the peer nodes? So please keep a note of these questions, because this would be part of the second bit. These would be I would answer these questions in the second part of my talk. And it is also very closely related to the performance. And when we talk of performance, it's like, how quickly I'm able to settle a transaction. And you might have observed that, in a Bitcoin, it takes, say, about 10 minutes. And then for just to create a block, but you need a confirmation of 6 blocks, which is about, 1 hour to settle a particular transaction. So how do we kind of minimize this information? How do we minimize the how do we resolve forks so that these questions or these problems do not arise in the first place? So these are the questions that we typically ask in the when we talk about performance. And one of the things that especially my team has been working on, that we have been working on, is how do we have a lot of off-chain transactions and minimum on-chain transactions, so that the performance is improved. And much of the work nowadays is focused on how do we improve the scalability and performance of these blockchain networks. And the last question that one of the questions that we typically ask is that what is the security, what are the aspects, security and privacy aspects or questions to ask? And I believe that, we had a session yesterday on the security and privacy of blockchains, which gave you some idea of what are the questions, so what are the issues, what are the privacy issues in blockchains, because apparently it seems that all my information is written on the blockchain. So where is my privacy going? Is it that people will know with whom I'm transacting, how much I'm transacting with? And to answer these questions, some of the things that I'm going to talk next will become very, very clear, like how do I ensure privacy and anonymity of individuals. Not only that, how do I hide the information that I write on the blockchain, because many of the blockchain implementations are public, or it's a public leisure. Not some are private, some are where you will not be able to see information apart from some of the parties, but many of the blockchains are open or permissionless, where all transactions are visible. So how do I guarantee privacy in those cases? So some of the tools that we typically use in these contexts is the hash functions, and it is a very, very important part of the blockchain, and I'm going to explain why. Digital signatures, which actually ensure that it ensures authentication or authenticates that authenticates a user who is either creating a prop or making a transaction, saying that, yeah, this is the person who has created this transaction. This is a miner who has created, or this is the entity who has created a block. And there are different types of signatures that are also used to enhance the privacy of various blockchains. For example, there are blind signatures which are used in the Monero blockchain, which actually prevent you knowing who has actually who has created a transaction when there is a pool of users around. So these are two very fundamental building blocks, and I'm going to talk about it next. There are also some importance of PRF, zero random number, pseudo random functions, and the construction of block ciphers, which is one of the very basic ingredients. And let's talk a little bit about the zero knowledge proofs, which are very, very important, which have become very, very important tools in blockchains. There are a number of reasons why these are important, and I'm going to give you some idea of what these zero knowledge proofs are and how powerful they are. So to start with, we'll talk about hash functions. So as to start with, the hash function is nothing less than a function. It's just a mapping where you have. Where is my cursor again? Just hold on. Stage. Stage is some reason. Stage. Kisan okay. So maybe I'll just proceed. Okay. So the hash function is just mapping. It takes a variable length input. So over here you can think of it as a string, any arbitrary length string. It's a binary string that we have considered. It could be some other set of alphabets, some other space, you can also say. And you have this hash function maps it to a fixed length string, which we call the message digest or fingerprint. The two important aspect of it is that if you are given message X, you can compute hash of the message to get, say, H of X to get Y, and this is easy. However, if you are given Y, X is computationally infeasible to compute, or I would say it is difficult to compute this X given Y. And this property is called the one-wayness, where you could actually compute one way, but you would not be able to invert. The other very important property is that of collision resistance. So it essentially says that it is very difficult to find two strings, x and y, which will hash to the same value. So if I have the hash function, if I hash hx and h of x dashed, it will be the same with very little probability. So it's very hard to find such strings x and x dashed which are not equal, so that they can map to the same value. And this is actually a very fundamental property that is used in various construction, and you will see that this is a very important property that also ensures how the immutability immutability property in the blockchain. There are various other properties that are also used, and I'm not going into that. What I'm going to do is that with the properties that I mentioned, it's a very very useful, very beautiful data structure called a Merkle tree. So the Merkle tree has been a cornerstone or a very basic building block in a lot of blockchains. And just to give you a little bit of a history, this was devised and patented by Ralph Merkle, whom I consider to be is a genius. As a part for signature scheme, it was done way back in 1979, and it's a very nice authenticated data structure. And I will tell you how it looks like. It uses the collision resistance property of hash functions, and how it does essentially is that if you look into the blocks, okay, let me try this. If you look into the blocks A and B, you take the hash of these two blocks and concatenate these blocks and compute the hash. Let it be I. Similarly, you do it for all the nodes. So take two nodes at a time, hash these nodes, concatenate this information, hash it, and ultimately you will get the root information. Now, notice that if you observe very closely, you would be able to see that given the hash value at any point, be it the root or an intermediate node, you will not be able to get what the block is. So you will not be able to get the messages, what is the underlying message. So if you even know what is HM1, you will not be able to know what is M1, because one side is easier. So given M1, it is easier to compute H of M1, but given H of M1, it is very difficult to find what is M1. So note that it's a very important property. So even if I had information about this, if this tree is public information, you would not be able to know anything about the underlying messages. Not only that, but the more important property over here is that this is collision resistant. So this is a very important property in this context of Merkle tree. This is a collision resistant property. So if you notice that if I change one of the blocks, say the C block, then what will happen is that in these cases, in the case of a Merkle tree, is that in a blockchain setting, the root information is made public. The root information is always made public, which is a reason. What happens is that if C is, for example, tampered, you have to the information, the jth information is tampered, and if the information about the node J is tampered, then the information about the node M is changed, and if the information about the node M is changed, then the root final value of the root is changed. So notice that even by changing one block, you will be able to, you are actually going to make an incorrect this final root information is changed, and this is a very crucial step, because Ultimately, these Merkle trees are, you need this Merkle tree for verifiability that all the blocks are intact. So what does a verification look like? If I have to say that the C transaction or the C block is correct, then I give to the verifier the information about the block D, about the block I, and the block N, and say that, look, I mean, these are the values that I'm giving you as a proof, and you can easily check this proof. And because you could actually have this information from C and D, you can compute the block J. You've given the block J and I, you will be able to compute the block M. And given M and N, you will be able to compute the root value and check with whatever is the public information. So note that if you change one of these blocks, for example, C or D, then this information will again change and it will not match with the root which is already published. So, and the good thing about this Merkle tree is that this can be done in the height of the order of the height of the tree, which is log n. So Merkle tree this makes Merkle trees a very useful and important data structure for most blockchain constructions. And this information, this Merkle trees are used in Bitcoin, Ethereum, and various other, not just blockchains, but various other file storage systems for verifiability of a lot of information that are in various contexts. So just if you forget about everything about this part of the talk, just remember that there is a very nice data structure, which is a Merkle tree, which is widely used in blockchains and many, not just blockchains, many other applications. Now, how is this blockchain or the Merkle tree used in the blockchain is that if you notice, and I'm pretty sure this might have been talked about in the previous part, is that, for example, this is a Bitcoin. This is how a Bitcoin blockchain looks like. Different blockchains have different realizations. Some have a linear structure. Some have it looks like a directed acyclic graph. It could be many things. So this is just one representation of a blockchain. And if you notice that in this particular representation, all these transactions are built as a Merkle tree and are kept in the Merkle tree. And only the root node is kept in the block. The root node is kept in the block. And notice that if one of the transactions is changed, then the root value has to be changed. Else, everyone can verify that all the peers can verify that there is something wrong with this particular transaction. This transaction is not matching because it is not matching with the publicly available information or at the root. Now notice that when I was talking that even if you can change one ledger in one block, you need to change it in all blocks. So note that somehow if someone has made a mistake and written an incorrect information in the ledger, in the Merkle tree, it could simply also change the roots. But if you change one root, then all the subsequent roots blocks have to be changed, because you keep the hash of the next block. You hash this block and keep this information in the next block. Now, note one thing is that, as I mentioned, that you cannot guess what the value of the block is from the hash of the block. So if you have the p hash, you will not be able to know what is the value of the block. And on the other hand, you cannot actually create another block which will also hash to the same p hash value. So that's the collision resistant property that we were talking about in the hash function. So this hash function is a very important concept that is widely used in blockchains. And the other property that is widely used is that of digital signature. So as many of you are aware that digital, just like you have a document and you sign it with your hand signature to verify that the authenticity or the of the documents and the signer, you typically sign also a digital document using a digital signature, and it can be publicly verified by anyone. And this is what it looks like more formally. You need a algorithm to generate some signing information and some verification information. So there is a signing key, which is a secret information, which is kept only by the signer. And there is a public information. This is over here, the PKA, which is used for verification. So there are two keys. One, when I say SKPK, mostly it is about secret key, public key, but notice that, make a note of it, that over here, SK is a signing key, PK is a verification key, PK is known to everyone, it is public information. SKA is known only to Alice, who is signing the document. Now, Alice uses this signing key to sign a message M and create the signature sigma over here. And Bob essentially takes the signature, and there will also be a message. So you need the message and signature. So there is a mistake over here. You need for the verification, you need the message, the signature, as well as the public information, the public key of Alice, or that is used for verification. So verification key. And if this is true, the verification succeeds, then we know that this Alice is the one who had actually signed this document. And if it fails, then we know that there is something wrong. And the security of this protocol is such that even if someone observes multiple messages and signatures, they cannot forge a signature on a new message. So that's the type of security that you have from these digital signatures. Now, note that this is also a very, very important concept that are used in multiple ways, and I'm going to mention some of it. The first place where this is used is that of that when you are creating a block, creating a transaction. So when you create a transaction, you say that yes, I am the one who has created the transaction. So there you sign. The other place where it is used is also the person who is generating the block, the entity who is generating the block, be it a miner or maybe it's something called something else. The block generator also signs the block, saying that, I'm the one who have signed the block. I have created the block. Now give me some incentive. Now, so the digital signatures are also very crucial to authenticate that the transactions have been properly generated and who is the person who has generated the digital signatures. Now, one question over here that is quite disturbing is that if you notice over here that this public information, the public key that I'm talking about, the verification key, which is the public information, everyone knows that this belongs to Alice. That this public key, the verification key, belongs to Alice. So that is the verification key and that of the entity. So this can create when it comes to the of the user of Alice, for example. And that leads us to the questions like, how do I protect against that? How do I make a anonymous? How do I say that, I'm not going to reveal my entity, I'm not going to say I'm Sushmita, I'm someone else. So one way of doing it is just have a different, have a pseudonym meaning that, I would have an alias saying that, this is alias, I'm publicly attached to that alias, which does not help to identify myself. But note that there are various challenges when you have these aliases as well. If I make a transaction able to crowd cost tracking for this, And these might be problematic. So multiple transactions could be linked to one person, and this is something that does not give a complete anonymity to various applications, blockchain applications. So this is not just a problem of blockchain, but it is a problem wherever you want to hide your identity. And if you just use a pseudonym, it's not good enough. The unlinkability problem has to be dealt with in a different way, which I'm not going to talk about, but this becomes a very important and interesting question to ask, that what are the different ways to hide my identity? And how do I ensure that not only I hide my identity, but I am able to unlink, or, to ensure that there is an unlinkability when it comes to various users making multiple transactions. So this is one question, and to some extent, different blockchains do it in different ways. For example, in the case of Monero blockchain, it was done using something called this was using something called a ring signature. In a ring signature, you will not know, you will have a ring or a number of participants, and you will not know exactly which participant created the transaction in that group. So that's one thing that that also helps to de-identify or an user in the whole scheme of things. The type of anonymity blockchain uses is pseudonymity, and there are various ways to get around that problem. I'm going to talk about one more technique which is called zero knowledge proofs, which are also very helpful in this. So I will take a little bit more time. I'm not going to talk about this, but I'm going to talk a little bit about zero knowledge proofs that are very important building block for ensuring privacy and of transactions. So what I'm going to do, I'll take a pause over here, and I will ask for questions before I proceed with this part. So maybe I can just now.
Thank you, actually, some people have written to me also. One person. Somebody has written, suggest me a good blockchain book. And another person, Anshu Bharti, has written, please explain digital signatures again. So these are the two questions that have been floated here.
Okay. So I have, oh my God. So I'm going to answer each of these questions. At the same time, I have also got some messages. Okay, what is apart from that storage capacity of a blockchain? So it is dependent, it varies from blockchain to blockchain, and so it could be 1 MB, for example, in Bitcoin. There could be other limits for other blockchains. So it is just, dependent on the blockchain, and everyone has some has a different value. So there is a question from Abhishek who writes that you mentioned that the data, we cannot put whatever we want in a blockchain, so what can we put in a block? What I wanted to say over here, maybe I'll just clarify what I mentioned, is that sometimes the data that you want to put on a blockchain, so the transaction data, for example, I mentioned that I have made a transaction from myself to my student, and the name of the student is, say, for example, Ram. Then I might essentially reveal two information, that I have made a transaction, and also maybe some of the value, or what amount of value I have made this transaction to, say, this entity. So this information, if I write, in some contexts it's particularly perfectly fine. In some contexts it might actually lead to privacy. So I would not like to do that, and therefore I need to actually not write the exact value to whom I have sent and so on. So it is just dependent upon the context, what you want to put on the blockchain and how you will put it on the blockchain. So there is no just a general rule that you cannot write this or you cannot write that. It is about the requirement that you have at hand. So many times most of the data is, if you have a sensitive data, you would not like to write it on the blockchain, and you need to either encrypt it or put some kind of metadata about the data. The metadata is also put for another reason, that if your data is very large and for example you want to send a large file and you would like to ensure that this information is kept on the blockchain, that it makes no sense because you are storing a lot of information in the block that you wouldn't like. So that's one thing. It cannot, so it just depends upon the context, what you can put in a blockchain and what you cannot. Okay, there is one more question. Is it hacked or not? Is it possible? Okay, it can be hacked or not. Yeah, I mean, honestly, everything can be hacked. Nothing is like, fully secure. So when you say hacked, it's difficult, and that is where the security comes from. Just to note that when we talk about the security, there is nothing like, we are not talking anything about the unconditional security over here. So please make a note of that. Now, what is a digital signature? Digital signature is a counterpart of your normal signature. So what you do in a document is that you have a document and you sign with your initials or your name or something. So in the case of a digital signature, it does the same thing for the same purpose. Now, digital signature is also, it will just look like a very random string, random information. The purpose is that looking into this random information and the message, you will be able to verify that the person has generated this random information. So that is what digital signature does and how it looks like. How it is constructed is there are different types, different ways in which you can construct a digital signature. And one of the things that you always keep in mind while constructing this digital signature is that what are my assumptions? What am I assuming when I construct this digital signature? And depending upon that, you have different constructions. So you have RSA signatures, you could have a DeFi, you would have the digital signature algorithm. You could have an elliptic curve digital CDSA algorithm and so on. So it could be anything. The construction will depend upon what you want. Do you want a short signature? Do you want a long signature? How strong you would like your adversary is who might break the signature? What are the underlying assumptions that are? So there's not one particular signature that is good or bad. There are a number of choices that you have. Many of the blockchain signatures use the ECDSA signature because of the size, if that answers the question. Can it possibly be possible to decode the hash function? I'm not very sure what you mean by decoding a hash function. So over here, the only thing that you would like is that given the message X, you're computing H, X, and Y. Is it possible to decode Y? I think what you meant is that given Y, can I find X? No, it's very hard. It's computationally very hard to do that. So yeah, that's what it means. Yeah. Yep. So there is one more question about hash trees and merkle trees. Yeah, this is one realization of it. But there could be other ways of constructing hash trees. Okay. What is a nonce in a block? Okay, so when you have, for example, when I had this, what can you see on screen? Do you see my slides?
Yeah, this is zero knowledge.
Okay.
Blockchain. Yeah.
Now I can tell you what a nonce is from this particular slide. So the nonce over here is not just a random number. It can be used only once. You don't reuse this. Over here, the reason it is used for is for a different reason. This is a Bitcoin blockchain. So in the case of a Bitcoin blockchain, you use nonce for a particular reason. So I have one slide over here that does that. I'm going to show that. So you can see a Bitcoin mining, a slide with Bitcoin mining. So typically what happens is that you might have come across this, that when a miner mines a block, then there are a couple of things that happens. So it checks the transactions and it checks that all the transactions are correct, and it also solves the puzzle, right? So this is something that I think this has already been told. Now, the reason this is actually done, the reason for doing this is that many people are competing to create the block. A person will be, or one miner will be given a credit in terms of the block bitcoins. Bitcoins are generated in a blind. Very competitive. There has to be one person who is a miner who's selected to be the block composer. And note that you have to make it like hard for a person to create a block, because there is a competition. Somehow you have to enforce that competition in the blockchain, in the ecosystem. Now, the way it is done is that you have to ensure that not only have you been able to verify all the transactions properly, you are able to also do some, show a proof of work, or here it is solve a puzzle. So different blockchains have different ways of ensuring that there is a consensus in the way the blockchain is formed. Now, one point over here is that how will you create that puzzle? So that there is the way to create a puzzle. So over here, the puzzle is a very simple puzzle. It tells that if you hash the block, and if the value is less than some system-defined difficulty level, which is we call Z over here, then the miner, this block will be a valid block, and you can actually get a reward for creating the block. Now, note that if you just compute the hash of a block, it's just a random-looking string. The hash function will generate a very random-looking string. There is no guarantee that this value will be less than the value Z that has been specified by the system. So the only thing that you have to do is that create the hash of the block and check whether it is less than the value Z. If it is not less than the value Z, then you create the block again and check it again. You go on with this process multiple times, doing it again and again and again, till you get a block that you that the hash of the block is less than some value Z. Then how from where will like create a block again and again? Because you have a fixed set of transactions, so that set of transactions are not changing. The breach value is not changing. The timestamp might change a bit, or it might be constant, depending on when the block is broadcasted. So you have only one variable. You can actually have one variable here so that you can change this variable again and again and again, create to generate a new hash every time and check value if it's less than. So that is why the nonce was introduced. That every time when you create hash and you have a previous hash, every time you choose a different nonce, check the hash, check if it is less than Z, and if it is not, if it does not satisfy this formula. And once you see that the hash of this block is less than the value Z, you just publish it. This is why the nonce was used in the blockchain, in the Bitcoin blockchain. That is what I got in the picture. Okay, so I think it is okay for the if you have still is a problem, then we could talk offline. Okay, there is another question: is blockchain security and privacy measures applied only on data storage and applications deployed on blockchain networks? Is the same security measures applied in plugin databases? Is blockchain really very secure or just a hype because every day there is a news of blockchain hacking? Oh, interesting. So the first part of the question is blockchain security and privacy measures applied only on data storage? No, not necessarily. Not just data storage. I mean, any kind of a transaction, it comes with an accompanying data, some information. It can be data about some financial information. It can be some data about who gives something to whom. So there is some associated data. One of the question is to have a security and privacy of data. The other question is that of the individual's anonymity, as I was talking about. Who is making the transaction, for whom the transaction is intended. That is also over there. You also have the question of security and privacy. So please make a note that this is what we are interested. These are the problems that we are interested when it comes to security and privacy. Not only that, there are various attacks on the network itself. For example, I could affect a majority of the nodes in some way by doing some kind of a partitioning attack, like having some nodes under my control, a sizable amount of nodes under my control, so that the transactions are not properly routed, not properly broadcasted. That could also be a very big form of a security problem in blockchains. There are various other problems. For example, when it comes to mining, how do I make sure that that people are doing this mining honestly? There are some questions around mining process which is called selfish mining, where the nodes where the mining process is typically done in an off-chain manner, and the attacker typically constructs the blocks off-chain, and then at a certain suitable point it just broadcasts all the blocks together in a network. And it has been shown that under certain conditions this mining can be very profitable, though not an honest behavior. So there are various types of security and privacy issues in the blockchain. There are issues around the mining pools. I'm not very sure if you have heard of mining pools in the previous lectures. So in the Bitcoin kind of a system, Ethereum kind of a system. There are miners who form pools, and these pools could be very these pools can be consist of number of miners doing this mining process, because as I mentioned that the mining process is typically very expensive process. You have to do a lot of these hash computations multiple times, gigahash, terahash, and so on. So this is very computation intensive. So people pull together their resources, and then some behave honestly, some behave dishonestly. So there are a lot of questions around security issues there in the mining process as well. Is blockchain really secure or not? Is the same security measures applied for plugin databases? Some of the questions are common. Some are there are each of these applications have each of these applications have their own challenges as well. Is blockchain really very secure or just a hype? So definitely there are some very interesting things happening in the blockchain space, and there is a lot of hype as well. So a good construction, a good implementation are really secure to a very high level. The good thing is that most of these blockchains are open to scrutiny, and some blockchains that were believed to be secure were later found insecure, either in the implementation or in the design. So these were rectified, or these were discarded. So I will not say there is not a yes or a no answer for this question, but I see a lot of hype as well, like people using it left and right when it's not needed. I don't feel good about that. Okay, now when using rings, they know who made the transaction. They don't know. That's a signature. Ma'am, please explain. Okay, again. Okay. Thanks. So many different origin transactions can be put. So there were two requests about the digital signatures and the Merkle tree. Since there are the time is limited, what I'm going to do, I will not be able to explain the Merkle trees again. But what I would suggest that if you have any questions, please write to me, and I'll try to provide some links for you. Okay. Now, can many different origin transactions be put in a single block? Yes. TX already hashed, so we need to encrypt again. So not necessarily. It all depends upon what you have kept, whether you have kept the transaction or just the hash. That's one thing. And also, in some cases, so typically it's the hash that is kept, so there's no need for encryption. But there are certain things that you would like to. So the transactions in general are not encrypted. So nothing is encrypted over here in the normal blockchain. That's nothing. So I did not essentially talk about encryption at all so far. Kindly see if you can explain a new block is created and who creates a block. If you can explain when a new block is created and who creates a block. Okay, a block can be created depending upon the blockchain in question. The block can be created by someone, might be anyone. In different types of blockchains. So this is actually a very interesting question, because different blockchains handle this in a very different way. So, for example, in Bitcoin, it is a miner who creates a block. Anyone can be a miner, can join the process, create a block, but it also has to do that amount of proof of work, which can be very tedious. In the case of certain other blockchains, for example, proof of stake blockchains, you could actually, this blockchain could be created by many other proposers. So um, mm, um, it is created by the blockchain who would have a fair amount of share or the stake in the system is a winner. And you have to do this in a way. You have to. No one should be able to guess who is going to be the next proposer, because if someone can guess, if they guess that I can be the next proposer, they can come and just kill me and not make me, create the block. So it is typically should look quite random, and there should be a way to validate that this block has been created by the right kind of people as dictated by the blockchain design. So I would say the short answer is that different blockchains have a different way. Who creates a block and how? When a new block is created. When a new block is created, when you have a substantial amount of transactions that you can put together and you would like to broadcast these transactions. Will you explain the scalability in terms of IoT? So IoT, it comes under different flavors. What you want to do with IoT and blockchain. So if it is like you are storing a lot of information about the blockchain, IoT data on the blockchain, then it's going to be really difficult for scaling it up. So you have to use different ways to ensure that not much information is written on the blockchain. You might also need for provenance, like who generates the data, or whether the device is authenticated, whether the right device is generating the data. So it all depends upon why you would need the blockchain in the first place, and whether this how this blockchain data is going to be used. So it will just depend upon what problem you are trying to solve. So just, that essentially makes me answer a different question, is that I have seen people using blockchains left and right for various things. So please make a note of it that if you have blockchains, it's like the first question to ask is that do I need a blockchain for what purpose? Does it essentially solve any problem that I'm not able to solve without a blockchain? Because note one thing, that blockchain means an extra overhead. You have to maintain a decentralized stuff, or you have to keep multiple copies of the data. You have to write on the blockchain, read from the blockchain. These are extra calls. So first question to ask, why I need a blockchain, what purpose it's going to be. Will I gain anything from having that design? And your performance will definitely be slower with a blockchain. So you have to ask is, what data I'm going to store. Is there any issue with the privacy on a block of a blockchain that we can't write anything particular there? Not very sure I understand the question correctly. Is there any issue with the privacy on a block of a blockchain that we can't write anything? Not very sure what you mean by that. Digital signature, which one key are you? Which one? This is something that I mentioned, is that you have a verification. We have a signing key and a verification key. Can powerful computers like quantum computers hack the blockchains looking at their computing power? Can they hack the digital signature algorithm? Yes, of course they can. That is why there is a lot of research going into designing and using quantum safe algorithms. When I talk about the zero knowledge proofs, I'm going to say that there are some constructions which are post-quantum, which are quantum safe. So there is actually a lot of research being done designing all these primitives that I'm talking about. Hash function is not a big problem because the public key algorithms are more affected. For the symmetric algorithms, you would just need to change. The algorithm does not have to be changed. Only the key sizes have to change. So symmetric key algorithms are comparatively safer. I'm actually very safe because nothing in the algorithm is changing. For the public key algorithms, the underlying assumptions will be our root cause of the problem. So new constructions are coming up in the digital signature schemes, for example, and one asks this question like, what works, what does not work, how much, what are the challenges, and so on. So, of course, there is an ongoing research on that. But this is a very good question that needs to be. There's no one answer here. Okay, so there are some very specific questions regarding, projects about e-health and so on, but I'm actually not answering because I'm not being able to proceed much in the talk. There is one more question on ring signatures that I mentioned before. All operations on the blockchain done by software, by any software operations in the software. So yeah, blockchain itself is the different blockchain realizations have their own software. So yeah, it's software.
If you like, you can go ahead, Sushmita ji, and
I think it's much
some people are very keen to
I think it's better if I go through the next part of the talk. Okay. So I'll give you a little bit hint about what the zero knowledge proofs are and why they are so important concepts, and why they are being if you ask someone that so someone is driving and you would like to know that the person is more than 18 years, how can the person say Alice prove that she is more than 18 years without revealing her age? Can we do that? Typically what would happen is that Alice would show out, take out her age proof and just show there's a lot of information written on the age proof, be it a driving license or Aadhaar card or something. So how would she prove that she is 18 years and above? So for example, driving becomes easy because you need a driving license. So if you have a driving license, you can just say, I have a driving license. If you don't, you just say you don't. Then you are in trouble. But if for other purposes, you want to have an internet account, maybe, or for some purpose, you would say that whether you are a child or an adult, you have to say something, right? So without revealing your age, how can you prove that you are suitable? So that's one question. Because the other question is that in the case of for example, look into the KYC that you always provide to your bank. There's so much information that's already there that's not required by the bank. But how do you say that I live at an address without revealing your address, for example? So you need to prove certain information without revealing anything extra. So that is where the zero knowledge proofs come in. So the party who is verifying should not know any extra information than just that you live in this you live in this particular state, for example. It does not need to know your address to verify. It just has to know that you live in the state. You did not know that. You should not be able should not be should not have to give your address altogether. So that's the type of information or evidence I would like to give to a third party for verification. So so these are what we call the zero knowledge proofs. Another example is that of the two people trying to figure out who is richer, and they exchange a number of messages. They ask each other some questions and answers, the other person answers, and without knowing the value of the wealth, can you figure out if there is Bob and Alice, who is rich amongst the two, without revealing the wealth? So the good thing about this whole, zero knowledge proofs is that you will be able to do that in some way. And the requirement over here is that the proofs should be so short and very quickly verifiable and very easy to construct as well. So what I'm going to do is that give you some examples. So I'll just skip through this. I'll just give you some examples where these are used in the case of blockchains. Okay. Yeah, so let me just tell this. So a couple of places where these are used in blockchain is that what is the value of the transaction? How can I hide the value of the transaction that Alice has made to Bob? How can I say that Alice has created this transaction? How can I say that Alice has transferred the current amount of money to Bob? How can I say that, or if it is to give to Bob and Charlie, how can I say that, Alice had X amount of money and it has given Y and Z, and these values are matching? I don't need to know that X, Y, and Z, but X is equal to Y plus Z is valid. It is correct. So the left-hand side is equal to the right-hand side without knowing what is X and what is Y and Z. So these are some of the questions that we typically ask. And if you were to hide the information of the transactions, you have to show that Alice has made this transaction to Bob and the value is hidden. Now, how will you verify that this value, typically when you pay from one account of Alice to another account of Bob, you also pay some transaction fees. So how can I be sure in the first place that this transaction, without revealing the value of the transaction, that it is correct transaction? So there are some of the blockchains which are called, for example, Zcash, which actually have these features. So it's not that these are completely fancy fairy tales or unachievable stuff. These are requirements, and these have been achieved. And these are done using something called zero knowledge proofs. So to start with, proofs, for example, are very fundamental to this whole concept of blockchains. Because if you remember in the definition of blockchain that I gave one definition, that is verifiable ledger, verify. When I say verify, it means that I have to give some evidence that is possible to check or verify. In the case of a blockchain, that is exactly what is happening. You are giving a lot of evidence that are stored on the blockchain, and someone, a public, a third party can verify, just looking into the blockchain data, that there is something that is going on. So one thing to note in this whole scheme of things is verifiability. So you give some evidence, the proofer gives some evidence, the verifier verifies that this evidence is right. So essentially, it is nothing but a proof. It could be a legal proof, which is some kind of an evidence that you prove to the court of law, for example. You could have authoritative evidence. You could have a scientific evidence. You could have a philosophical evidence. You could have lots of types of evidences or proofs. you have also seen that in from a very from your school days that you have a mathematical proof, so you have a set of axioms, and from your axioms you make some deductions, and you come to a conclusion. You also call proposition. So ultimately, you have to with a set of axioms, you derive that the proposition is true or false. So these are different ways in which we think of proof. There are different ways in which different people prove different things, and the type of proof that we will need in the case of a blockchain is that proof that A made a transaction to B, proof that A's transaction that he gives to C and D is correct, proof that there is no double spending, proof that A is a valid person. So there is always some kind of a verifiability that is there, that is happening. And if you just think of, forget about financial transactions, forget about all these transaction, you want to verify that the computation of a scientific result is correct. You need a series of steps to verify that, without redoing the computation, you are able to verify that A plus B is equal to C. So suppose you are doing an enormous amount of computation, scientific computation, there's lots of data to be involved, which is done possibly by a third party. You don't know whether the third party is returning you the right result. You need to verify that the proof is, or the result is correct. So there is a lot of question about verifiability when it comes to blockchain. It is a very fundamental question to ask. And proofs are very important for blockchains because it has the verifiability property. One of the things that typically happens in the blockchain scenario is that how do I give short proofs? Short proofs, when I say short proofs, like make short the proofs that look like some strings actually, and the shorter the size of the proof, the better for me, because often you might essentially broadcast this proof, and ask the verifiers to verify that this information is correct or wrong. So you need this verification to be very fast because this is done by multiple peer nodes. Verify that A made a transaction to B and the value is correct. A did not steal anything. B got what it was promised. Everyone verifies in the network. It has to be very quick. It has to be very quick. It has to be very short. If you block the network with a huge amount of network traffic, then nobody will like it. So these proofs have to be very short. So that is where the proofs essentially come in. And in the next part of my talk, I'm going to give you specific examples where what these proofs look like in a storage kind of a setting. And the next thing to consider is that not only do I need these proofs, I need to make them zero knowledge. So I'm coming to what it makes to a zero knowledge. But before that, when you come to a proof, you have a statement actually. You have a statement. You have to prove something. Is Alice greater than 18 years, for example? Or does X belong to the set L? X is a string, does it belong to a language? Now, note that you give a proof, and the proof systems that were initially developed, these were done in mid-80s by very, very seminal work that were done. So there were two things that you have to ensure. So first thing is that you have to ensure that if you would like the X, for example, a membership in a language, so X belongs to this set L or not, you need completeness, meaning that you would have a proof such that the proof with the value of X or the string is correct, is acceptable, by the verifier. So you have a prover who will generate the proof, and the verifier will verify the proof. So for completeness, you would like to ensure that all valid membership proofs are correct. And if X does not belong to the language, then verifier will reject that proof. So that is what we would like to have in the system. So a proof is correct, or this proof system, the proof is correct if, for all instances, the prover is able to convince a verifier that this is the correct proof. And if membership is not, if X is not a member, then it should not be able to prove correctly. So I'm not going into these details, but one more thing is that this should be done efficiently. So when I say efficiency, the verifier should be efficiently able to compute, or not to compute, but verify the proof. And this is done in polynomial time. So when I say polynomial time, it means that a polynomial in the size of the input X. So note that there are a couple of issues over here, and one of the things to notice that efficiency is a big factor, and I'm going to say how very important it is in the case of blockchain. Now, when I was talking about proof, there is typically an interactive proof. You ask me some question, I answer. So in order to find some interesting information, for example, which place I visited last weekend, I might not essentially tell you exactly, but you might try to so you might essentially ask me various other questions. So this is a question. So this is a membership thing. So let's ask, did I go somewhere during the weekend? So you might ask me multiple questions. Did you clean your house at this time? I say no. Okay, then that means that there is a possibility I did do something else. So there are a large number of questions that the verifier is shooting. So it is an interactive process to figure out whether the statement is correct or wrong. And these are called the interactive proofs. So verifier asks a query, the prover gives an answer. The verifier asks for another query, and the prover gives another answer. And depending upon this, you finally come to a conclusion, depending upon the answers, whether it is right or whether the verifier should accept or reject. So whether the statement is correct or wrong. So these are the interactive proofs. However, there is one thing that is really important in this definition. So one of this is completeness, meaning that if you have a prover and a verifier, so the verifier will accept the statement if it is correct with a very high probability. And soundness says that if the proof is incorrect, then it is going to reject with very high probability, or it's going to accept with very little probability. And this is exactly what we typically do. So, for example, in the previous case, think of it that you have an interactive proof. So you're doing an interaction, and you're repeating this process. So if I don't have a proof, if the X does not belong to the language, I will not be able to give a proof at I'll fail at multiple instances. So I might pass in some instances, but I will fail in multiple instances, and that's where the verifier will know that this is this proof is not right. So maybe just give you an example of where the zero knowledge comes from. So proofs, need not be zero knowledge, because I might say that, look, I need to color a graph with 4 colors, and I give you the coloring. That's it. So you ask me whether the graph is given a graph, whether it's 4 colorable. Do I know if it is 3 colorable or not? I say, okay, yes, this graph is 3 colorable, and I know the coloring. So I tell you that, okay, look, I know the coloring. Then Bob says, you know the coloring? How do I know that you know the coloring? And one way is that I tell him, works is that I can disclose a lot more information about the whole process. So just giving one example is that if I were to, if the prover here, Alice, says that, whether X is a quadratic residue modulo N. So quadratic residue means that, if you have X, you can find another element, Y, which is such that, X is equal to Y square mod N. So is X a quadratic residue? So first thing that Alice could do is that give a Y and tell, the proof is Y. And how will Bob check it? Bob will just compute X, just compute Y square, just look into X, compute Y, W square, and just check whether they are equal. But note that in giving such a proof, Alice is giving lots more information. She only has to say whether X is quadratic residue or not. Instead, she is actually giving the value of another value, which is not required at all. So this particular thing reveals a lot more information to Y what V can compute. So this question actually makes us ask is there a way to actually give as little information as possible? Now, so I know that there are some questions, but I'm going to take questions later because that is what I have been told after a while. And I'm going to break in another 10 minutes. Yeah. So no knowledge should be leaked. That is what we leaked, is that we didn't learn W at all. The verified did not learn anything about W, or if it learns only one bit of W, that is also an extra information. Or it did not learn anything about W. It did not learn, say, W square. It did not learn F of W. It does not learn anything about W. Or it did not learn anything else except that X is a quadratic residue, mod N. So when I say that no knowledge is leaked, it means that whenever you have when you have a computation, the interaction should not reveal anything that you would have without computing it. So if the following interaction Y could compute anything, compute something that he could not have computed without, then that is what we typically require. And what it means in our case of a blockchain is that I will not reveal any information, any value of the transaction, but I would be able to show that the transaction has been made from Alice's account properly to Bob and Charlie. And, there is no cheating, nothing happening in the middle. So I will not know what value Alice has set to Bob and Charlie, but I will know that this is okay. Everything is fine. Alice did not spend more from her account, and the value actually matched. So matched with the X plus Y, the value that Bob and Charlie has received. It is just fine. So these are the questions that we ask when zero knowledge is concerned. And as I mentioned, that these proofs should be really short and quick to verify. So one of the things that is really important, so I'll just try to address this question because this is something that is very important in blockchains as well, which is the concept of commitments. And here the commitment serves two purposes. So when you are making any transaction, you are committing it to the blockchain. You're writing it to the blockchain in such a way that you cannot later deny that you have done you cannot. So commitment essentially means that you are some kind of undeniability in this particular case, but it does many things. Two very important things. So imagine that you have a message that Alice writes, and she puts it in a box, and locks the box and sends to Bob. Now there is no retracting. Alice cannot deny that I haven't sent it, because now she does not have the box at all with her. She cannot just change it in any way. But note that this is hiding. It hides the information that Alice has written, the message that it has written. And Bob does not know anything about it. So that is the question. That is this. That is already committed by Alice, and it is also hidden. Now there is something called an opening or reveal phase. In this case, the key is given by Bob, and Bob gives the key to Alice, and then Bob opens the box and reads the message. So that is an opening phase, which happens at a later time. Now note that very important aspect of it is that now that Alice has sent this box with the locked box, she cannot deny anything. At the same time, this is hidden until at a later stage you have given some extra information to open up this thing and figure out what it is. So these commitments are often used in blockchain in various ways. So for example, how can I say that I have made a transaction? So I will say that, look, I am making a transaction. I'm putting a commitment that, this data has been sent from me to other person. Later, I will not be able to deny it. I will be able to possibly hide this information. And later, when I need, I can open up and say that, look, this is evidence that I have. I can show that I can open it and show that, yes, this is what I had written. So commitments are very important when it comes to blockchains because of these factors. And just going back to the zero knowledge, I'm going to give you just one example before we pause and take a little rest, is that the question of graph coloring. So Alice wants that the nodes of a graph can be colored with at most 3 colors, so that the adjacent nodes have different colors. So this is a very well-known problem. One way to do it is that send the colored graph to Bob, but that reveals a lot of information about the coloring itself, so that's not desirable over here. So I'm trying to give a zero knowledge proof that the graph can be colored with 3 colors. And Alice knows such a coloring. Not only that the graph can be colored with 3 colors, but Alice knows the coloring. So these are 2 important things to keep in mind. And Alice is proving, look, I know the coloring over here without revealing the colors. So this is something to make a note of. So what she does is that, just like before, she takes the graph, colors it, and then, hides each of these colors using the commitments that we talked about before. So it's like putting it in the boxes and sending it to the verifier, Bob. What Bob does is that it makes a query. It tells Alice, look, I want this red colored edge. You open the red color edge for me. So it sends this red color edge that you see on the right hand side. It says that, look, open this one. And so Alice sends the opening or the key to these boxes, to these 2 boxes, this particular 2 boxes over here. And then what happens is that Bob opens and sees that these 2 colors are different. So that's a good thing, right? So if these 2 colors had been the same, then the test would have failed immediately. So Bob knows that these 2 colors are same. So possibly Alice knows, but it could be the other way around. Like, he was very lucky, and Bob chose the right colors, which were actually non-adjusted adjacent nodes with two distinct colors. But it's possible that the other nodes are not same, not colored properly. So what happens is that what Bob could do now is do this multiple times. So the next round, he chooses another edge and asks Alice to open it. Alice sends the opening, and Bob checks again and again and again, and every time it should pass the test. Note two things over here. If I were to do multiple times, and if it was, I could actually know all the colorings, right? So the trick over here is that you will do the process fresh every time. So color it with a distinct set of colors, with random colors, encode it, or I would say commit, send it to Bob. Bob chooses a different edge and asks Alice. Alice gives the opening. Do it again, color it again, independently than the previous round. Do the same thing, commit, send it. Choose, Bob chooses maybe possibly a different edge, asks Alice to open it, and so on. So every time independently you do it multiple times, then, with a very high probability you will succeed to get, it's like very difficult for Alice to guess which edge Bob is going to choose and color it appropriately. So this should work. The last thing that I'm essentially going to say is that I'm not going to say everything, but the interactive protocols, if I were to do the same thing, try to verify some information on the blockchain using such an interactive process, then it would be very, very time consuming. So what I'm going to do is do it in a non-interactive fashion, and much of the discussion, research, and everything is around this. Like, how do I efficiently design protocols that I can do in the non-interactive setting? So there is a very well-known transform called the Fiat-Sushmita transform that will take an interactive process and make it a non-interactive process. So now Bob will make one query, and Bob will not make one query. There will be no such queries or anything of that sort, but Alice will be able to give a proof to Bob, and Bob can verify without going into that interactive process with Bob. And that is desirable because that saves you a lot of communication overhead. So much of the work is designing, much of the things that people are doing is to do this proofs in such a way that these are really short and easily verifiable and quickly verifiable. And just to give you an idea of what these look like, I'm not going into the details of all the technical stuff, but the only thing is that whether you have a security in the post-quantum setting or not, in the post-quantum, whether it's post-quantum safe, what is the size of the proof, what is the verification time? Please, let's forget about these parameters over here. But not over here. Please focus on the sizes. Most sizes, the desirable thing is over here, the sizes and the verifier time. Here, n is something called the depth of the circuit, which we don't need to think about now. There are also different ways to generate the proofs in different models. So, but ultimately, we need very short proofs, and this is one of the things that people are also noticing or observing or trying to figure out. So I will stop here and maybe take a few minutes break and come up and talk a little bit about storage and blockchains and some interesting problems there. And the questions, I see not many questions. Yeah. So how long should we break for? So let's stop here and then return in some 10 minutes or so.